Paper 2 from November 23, starting off with defining the term homologous series. We see this term in organic chemistry to refer to a family of hydrocarbon compounds with the same functional group and therefore general formula. So we will start off by answering family of compounds with same functional group as well as general formula. What else can we say about homologous series? Homologous series like alkanes, alkenes, alcohols, they all have similar chemical properties. They undergo the same reaction types, reaction mechanisms. They also have varying physical properties, gradually changing with increasing size, decreasing size, where the differing hydrocarbon units will be CH2. Moving on to the next question, we are looking at methanoic acid, and we're going to find the percentage by mass of oxygen. 2 oxygens in 2 hydrogens. 1 carbon and 2 oxygens. If we do the math, we will get 69.52%. Obviously, provided we multiply the fraction by 100. Comparing methanoic acid with ethanol, which have similar molar masses and therefore similar magnitude, similar size of London dispersion forces. If they have different boiling points, it means intermolecular forces other than London dispersion forces must be different. The reason behind methanoic acid having higher boiling point is methanoic acid has hydrogen bonding. Methanoic acid has hydrogen bonding, while ethanol only has dipole-dipole. And which is stronger? Hydrogen bonding is stronger. Ethanol and methanoic acid are both soluble in water because they are polar molecules. But the question states fully miscible. It's beyond soluble. It's mixing very well, in other words, interacting very well with the solvent water molecules. And that's probably because hydrogen bonding is available definitely between methanoic acids, but also ethanol as well. But did we just not say that ethanol does not have hydrogen bonding, but dipole-dipole only? Well, by definition, hydrogen bonding is what? Electrostatic attraction between the hydrogen bonded to an oxygen and an oxygen. Yes, ethanol cannot have hydrogen bonding with another ethanols because we do not have the OH interaction where H is bonded to an oxygen. But if we had water around ethanol, the hydrogen that interacts with the oxygen of ethanol is bonded to oxygen. Therefore, the interaction between water, solvent water molecules and ethanol, by definition, is hydrogen bonding. Hydrogen bonding. Comparing methanoic acid, ethanol, and hydrochloric acid. For electrical conductivity, we want to see how well the compounds dissociates into ions. We know hydrochloric acid will fully dissociate into H+ and chloride ions. Completely dissociates, meaning if we have 1 mole of hydrochloric acid, we'll end up with 1 mole of H plus and 1 mole of Cl minus. Therefore, HCl will have the highest electrical conductivity of all, followed by methanoic acid. Why methanoic acid? Weak acid. A weak acid that partially dissociates into H plus and the conjugate base methanoate ion, with ethanal being the least electrical conducting solution. In fact, ethanal does not dissociate at all. But does that mean that ethanal does not have any electrical conductivity at all? That's not true. There is some electrical conductivity in ethanal solution due to water solvents. Water solvents will dissociate partially into H plus and OH minus, which confer ethanal solution some electrical conductivity, but no electrical conductivity due to ethanal itself dissociating. HCl fully dissociates into H plus and Cl minus. What are these? These are mobile ions, freely moving mobile ions. CH3, HCOOH partially dissociates into H plus and methanoate. Ethanal, CH3CHO, does not dissociate into any of the mobile ions. To find the mass of methanoic acid used to create 2 dm cube of methanoic acid solution, we first need to find the amount of methanoic acid. To find the methanoic acid, we will utilize the information of sodium hydroxide amount used for titration. However, the amount titrated only corresponds to 25 cm cube of the 2 dm cube solution. Therefore, what we're going to do is work out the concentration of methanoic acid, and we're going to multiply that concentration by the volume 2 dm cube to work out the mass, the amount of methanoic acid, total methanoic acid used. So the amount of sodium hydroxide is going to equal to the amount of methanoic acid in 25 cm cube, which can be written as 0.0207 dm cube multiplied by 0.1. Then we're going to work out the concentration of methanoic acid by dividing the amount by 0.025 dm cube. To work out the amount of methanoic acid in 2 dm cube, we're going to multiply the concentration we've calculated by 2, which, if we do the math, will give us a value. But the overall purpose of this calculation is to work out the mass, for which we're going to further multiply the value with the molar mass of methanoic acid. And what's the molar mass of methanoic acid? It's going to be 46.03 grams per mole. So if we do the math, it would give us 7.62 grams overall. pH of methanoic acid solution can be calculated easily. How? Well, we know the initial concentration because we've calculated the concentration to be right here. And if we refer to the data booklet for the pKa value to work out the Ka value, we can work out the H plus concentration value. Ka for methanoic acid is going to be HCOO methanoate concentration that equals to the H plus concentration. In other words, we can rewrite Ka equals H plus concentration squared over methanoic acid concentration. Now, Ka value for methanoic acid is going to be 3.75. 3.75. Therefore, methanoic acid pKa would be 10 to minus 3.75. We already know the concentration of methanoic acid, which we have calculated to be 0.0828. So if we do the math, H plus concentration is going to be 3.84 times 10 to minus 3 mole per dm cube. So pH is going to be minus log H plus concentration, so that we will have the overall pH value of 2.42. Sodium methanoate is a salt. It's a salt from neutralization of what we presume to be the parent base sodium hydroxide and parent acid methanoic acid, a weak acid and a strong base derived basic salt. How do we know that? Firstly, drawing a titration curve, we would expect how titration curve would start at a pH higher than 1 and would end up with pH near 14, meaning that the equivalence point would be at pH higher than 7. That's how we know the pH of the salt would be higher than 7. To prove that it's higher than 7, we will take methanoate ion, which we know to be a strong conjugate base. Because the methanoic acid was a weak acid, we know the conjugate base would be a strong one. Hydrolyze methanoate to give weak acid, methanoic acid back, as well as OH minus. Now, the OH minus produced is what renders the basicity of the sodium methanoate salt. So we know pH would be greater than 7 due to the hydroxide ions released from hydrolysis of the methanoate ion. If we draw methanoate ion, we would draw the following. How? There's a double bonded oxygen as well as a single bonded oxide. However, there is room for delocalization. The room for delocalization allows presence of resonance. And resonance means that the carbon to oxygen bond will be halfway in between single and double bond, will be partial double bonds with bond order of 1.5. Therefore, due to the presence of resonance, we have equal carbon to oxygen bond length that are partially double bond, halfway between single and double. Bond length 1.5 can be added. Hydrogenation of carbon dioxide can result in formation of methanoic acid. Well, this, if possible, would be a great way to remove carbon dioxide that's the culprit behind global warming. Carbon dioxide is best known for greenhouse gas that contributes to global warming, and if we can remove by any means, would be a great way to make the environment better. So CO2, greenhouse gas, may be removed to reduce, alleviate global warming. Equilibrium constant expression would be Kc equals to product methanoic acid concentration over the reactant concentrations, CO2 concentration multiplied by the hydrogen, H2 concentration. Delta H for hydrogenation of methanoic acid may be deduced by looking at the bond enthalpies of the reactant particles as well as the products. Let's start off with CO2. CO2 has two COO bonds, while H2 has one H2H single bond. This results in methanoic acid that has one COO, one carbon to oxygen single bond, one oxygen to hydrogen single bond, and finally one carbon to hydrogen. All we now have to do is look up the data. We'll go to section 11 and work out how carbon to oxygen double bonds has 804. kilojoules per mole, but we'll multiply the number by 2 because there will be 2 carbon to oxygen double bonds. Hydrogen to hydrogen single bond is where? Hydrogen to hydrogen is right here, 436. 436, there will be 1. Carbon to oxygen double bond, there will be 1. Carbon to oxygen single, there will be carbon to oxygen single, 358. OH, O2, hydrogen, 463. And carbon to hydrogen. Carbon to hydrogen, 414. Let's sum these up so that we have the equation delta H, that's hydrogenation, delta H, as sum of bonds broken. Now that's the sum of the reactant bond enthalpies. Take away the sum of the bonds released. Sorry, bonds formed, not released. Energy will be released from bonds formed. If we do the math, we will end up with bonds broken. Sum of bonds broken will be plus 1240. Take away 1235. That gives us overall only 5 kilojoules per mole. That's unusually small delta H value. Assuming 1% uncertainty for each bond enthalpy. Okay, so bond enthalpies are assumed to have uncertainty, percentage uncertainty values, and that's 0.1%. Determine the resultant percentage uncertainty of the calculated. So we're going to have to find the percentage uncertainty for delta H, and to do that, we're going to have to work out the absolute uncertainties for each bond enthalpies, add them up, and then find the percentage uncertainty. So to do that, what we're going to do is multiply 804 by 0.01. 0.001, which corresponds to 1%. That would be 0.804. 0.436. Again, 0.804. 0.358. 0.463. 0.414. Let's sum all these absolute uncertainties together. That would be 0.804 multiplied by 3 plus 0.436 plus 0.8, we've already taken that into account, 75358 plus 0.463 and 0.414. If we do the sum comes out to be 4.083. Now, the unit is going to be kilojoules per mole. And what we want is the percentage uncertainty that arises from 4.083 out of the delta H we calculated, which is 5 kilojoules per mole. This is quite high. That comes to 81.7%. 81.7% is quite high, and because we are dealing with one significant figure for the percentage uncertainty, we also need to deal with one significant figure so that we will end up with 80% percentage uncertainty. Yes, bond enthalpies are usually only approximate values because they are averaged over many different compounds. Therefore, they are usually inaccurate. But one of the bond enthalpies we dealt with is going to be accurate, and that's going to be what? Hydrogen. Why is hydrogen to hydrogen bond enthalpy value accurate? Well, it's because hydrogen to hydrogen bond enthalpy value cannot be averaged. It only exists in H2 compound, H2 molecule. Sorry, H2 is not a compound, H2 molecule. Hydrogen to hydrogen bond enthalpy value can only be derived from one molecule, that's H2. Because the value only exists in one molecule, that is H2. Temperature change would definitely affect the value of Kc. Temperature increase will be counteracted by decreasing the temperature. That is possible by favoring the endothermic forward reaction. However, the resulting position of equilibrium lying towards the product side will be very minute. Why? Because the delta H value itself is very small, only plus 5 kilojoules per mole. Delta H value too small. Entropy change value can be calculated by having the sum of product entropy minus the sum of reactant entropy. We have the entropy values for hydrogen and methanoic acid, but we are missing the entropy value for our carbon dioxide. So let's go and look up the entropy value as the value of plus 213.38. Therefore, we can say delta S equals to 251.0 take away 13.7 take away 213.8. In total, we will end up with what value? Minus 93.5 joules per mole per Kelvin, the unit for entropy. Drawing the energy profile diagram, where we start off with carbon dioxide hydrogen reactants, we'll have to draw our product, methanoic acid, at higher potential energy than the reactants. Why? Because we are dealing with an endothermic reaction where delta H will be a positive value. But of course, the positive value is only 5 kilojoules per mole, so quite a small delta H. So it may be more accurate to actually lower these guys, and it will be more accurate to indicate a very small delta H value. However, there will be yet higher potential energy state of our reactants, and that we call transition state. Transition state. Which will have energy difference with the reactants, which we refer to as the activation energy. And the energy profile diagram is completed by having a curve that joins reactants, transition state, and the methanoic acid product. If we add catalyst, what happens is the activation energy is lowered, is reduced. And that's because catalyst provides an alternate reaction pathway, meaning that we'll have a new activation energy. If we call the activation energy uncatalyzed, we can have another activation energy that's catalyzed, EA catalyzed, which means the transition state has lower potential energy, and therefore we have a lower peaking energy profile diagram. Factors that affect the reaction rate include temperature, concentration. Concentration is for liquid. We can introduce the idea of pressure for gaseous reactants, which applies to our case. We have the gaseous carbon dioxide reacting with hydrogen. Therefore, pressure is a factor that could affect the rate of reaction, not concentration. We would have surface area. Surface area would only apply to solid state reactants, so not applicable in our case. Catalyst, we've already looked at. So besides temperature, pressure is the only factor that would lead to change in reaction rate. And if we want to increase the reaction rate, we need to increase the pressure. How does increasing pressure lead to reaction rate increase? Well, collision frequency needs to increase. Collision frequency can increase by having the reactant molecules more closely packed, more densely packed. Reduce the distance between the reactant particles so that they don't have to travel as much. They need to travel just a little bit for collision. So collision frequency increases, successful collision frequency will also increase, leading to reaction rate increase. Methanoic acid, HCOOH, has the electronegative oxygen that takes -2 oxidation state. 2 oxidation states in total, -4, that are going to be balanced by 2 hydrogens, 1 plus each, meaning carbon needs to contribute 2 plus oxidation state, plus 2 oxidation state for carbon. Methanoic acid, as a carboxylic acid, can react with an alcohol to produce ester, as well as the byproduct water. This reaction we call condensation because water is being condensed out. The reagent for this reaction, when we have methanoic acid known, will be methanol. The alcohol, methanol. Will be an alcohol, but we know it's going to be a methanol because the ester we're dealing with is a methyl methanoate. We're given that the ester produced is methyl methanoate, meaning methanol and methanoic acid have reacted. The catalyst would be sulfuric acid, H2SO4, and we want to make sure that we use concentrated. Apparently, we're not producing 100% of the ester as we expect. We expect there to be 1-to-1 molar ratio of methanoic acid and the ester. Why is that? It's because HCOOH reacts with CH3OH to produce HCOOCH3. We're dealing with 1-to-1 molar ratio, and that means the amount of HCOH should equal to the amount of our ester, which clearly doesn't, which clearly will be less than the amount of methanoic acid. And we're going to find the percentage yield. How do we find the percentage yield? Percentage yield is going to be the actual over theoretical, expected. Actual being the ester amount, expected being the methanoic acid amount. What's the amount of ester produced? Well, we're given 1.72 grams, the mass of methyl methanoate. All we need is the molar mass. All we need is the molar mass information of methyl methanoate. If we work it out, 4 hydrogens, 2 oxygens, 2 carbons, do the math, we'll be given 60.06 grams per mole value, which will be divided by the amount of methanoic acid, where we're given 2.83. 2.83 grams divided by the molar mass of methanoic acid, 46.03 grams per mole. Let's do the math, and we'll be given 46.5%. That's quite low percentage yield. Both methanoic acid and methyl methanoate are colorless, but we can differentiate between the two by using IR spectroscopy because the readings will be different due to different groups present. Both of them will have carbonyl group. Let's draw the structure of methanoic acid as well as methyl methanoate. Both have carbonyl. And what's the reading for carbonyls? Carbonyl at 1700 to 1750. Don't bother looking up the infrared IR data. Just know, you just have to know 3 readings, right? Carbonyl, hydroxyl in alcohols, and hydroxyls in carboxylic acid. Where the carboxylic acid will have the reading of OH group in carboxylic acid will have the reading of 2500 to 3000. In methanoic acid only, absent in methyl methanoate, will tell us, will give hints to differentiate the 2 reactant end product. NMR data. We unfortunately do not have the NMR data, but we can expect what they will look like. The question is asking us which one the data would refer to. Well, we can get both NMR spectrum to look like. We would expect for methanoic acid 2 signals, 2 peaks. We would also expect 2 peaks for methyl methanoate. But for methyl methanoate, we have more number of hydrogens, which means that the peak intensity will be greater. 2 peaks for both compounds, where one of them will have 1 peak that is 3 times bigger than the other. So we would expect methyl methanoate to have one of the 2 peaks to be 3 times bigger. Of course, we could look at the chemical shift value as well, but the question is not asking us to do so. Methyl ethanoate, methanoate obviously is an ester. Carbon disulfide is like carbon dioxide, where carbon is double bonded to 2 sulfur atoms, where each sulfur will have 2 lone pairs. So both carbon and sulfurs are happy with full octet. Water can be added to carbon disulfide to produce carbon dioxide and hydrogen sulfide, for which we will calculate the delta H. We're given the delta H formation values for some of the reactant end products. If we have the data for the rest of the reactant end products, we can set up Hess cycle and work out delta H. Let's look up the values for H2O and carbon dioxide. We'll go to data booklet, where we will have data for water and carbon dioxide right here. Minus 285.8 kilojoules per mole, and carbon dioxide 393.5. 393.5 minus delta H equals to sum of delta HF products minus the sum of delta H formation of reactants. Now, for some reason, if you don't remember this formula in the exam, you can work out this formula. How? Set up the 3rd list of constituent elements of the reactant and particles below the equilibrium sign as carbon, solid, sulfur, gas, and sulfur will be existing as solid in standard state. So sulfur solid, and oxygen gas, hydrogen gas. And what we say is, to form carbon disulfide, we would be inputting 88.7 kilojoules per mole. To form water, we will be releasing 285.8 kilojoules per mole, but we're going to have to multiply that number by 2. Why? Because by definition, delta HF is the enthalpy change when 1 mole of water is formed, not 2. Which means if we're dealing with 2 water molecules in the reaction, the delta HF value needs to be multiplied by 2. Carry on to have carbon dioxide as minus 393.5, and finally 2H2S. Like water, we'll need to multiply the delta HF value for H2S by 2. Then delta H will be minus 88.2, 88.7, minus bracket minus 285.8 times 2, plus minus 393.5, plus minus 20.6 times 2, which equals to delta H equals sum of delta HF products minus delta HF reactants. I'm going to save myself having to write all these, having to calculate all these values, and I've pre-worked out the value to be overall minus 39.8 kilojoules per mole. The entropy change for this reaction is apparently quite small. Would it be? Let's have a look. 1 mole of carbon disulfide, 2 moles of water, gas. Wait, hang on. I think we made a mistake. H2O is in gaseous state, not liquid state. The delta HF value we should have used should be for steam, not liquid water. Apologies. We should have used 2 for 1.8. Be careful. H2O delta H value exists in 2 values, one for gaseous water, one for liquid water, and the one required for our question is 2 for 1.8. Do not make the same mistake I made. So there are 3 gaseous reactant species that become 3 product gaseous species. For entropy to be largely positive or negative, there needs to be significant number of moles of reactant and product species, as well as change in the state from unordered to a disordered, or disordered to ordered. In our context, we have equal number of moles for reactants and products that are all in gaseous states. Therefore, entropy change would not be very high. Equal number of moles of reactant and product species, all in gaseous states. Neglecting any entropy change, work out equilibrium constant. Equilibrium constant from delta H value only? It's not possible, but it's possible if we do a pre-step, another step beforehand, where we work out delta G. Because delta G can be worked out from delta H, minus T delta S. Unfortunately, we are not given the delta S value, are we? We just know it's going to be quite small, which we can neglect. So what we'll assume is that we'll assume T delta S is 0, meaning that delta G equals delta H, which we have calculated to be minus 39.8 kilojoules per mole. From this value, we can now go on to say that delta G equals minus RT ln K, where ln K can be represented as delta G minus RT. If we do the math, it would be minus 39.8 kilojoules per mole over minus 8.31. Gas constant has unit of joules per mole per Kelvin. Therefore, we'll have to equalize the unit for energy in joules. So I'm going to convert 39.8 into 39800 joules per mole. Again, back to the denominator. The gas constant times, we were given a temperature specifically 500 K, where we will have cancellation of some units. Kelvin will cancel out. Joules per mole values will all cancel out. And if we do the math, ln K would work out to be 9.58, so that K, we know, will have the unit of exponential 9.58. That value is going to be quite high, 1.45 times 10 to the power of 4. At equilibrium, we are given specific concentration values for the reactant particles, but for the product, unknown amount, but we know that there will be 2 times more H2S than CO2, as indicated by the stoichiometry of our reaction. Kc value can be represented as concentration of the products, but H2S will be squared and CS2 concentration as well as H2O concentration, but squared. Let's input the values in. The values would equal to x times 2x squared. Now be careful, 2x squared is not 2x squared, it's 4x squared. Therefore, overall, 4x squared over 0.04 times 0.1 squared. Overall, Kc, we know, is 1.45 times 10 to the power of 4. And if we do the math, x is going to be 1.45 times 10 to the power of 4 multiplied by 0.04 times 0.01 divided by 4 and then square rooted. So that x is going to equal to overall 1.13 mole per dm cube. We have drawn carbon disulfide molecular geometry beforehand. How? We have carbon double bonded to 2 sulfur atoms in a linear molecular geometry. We call the molecular geometry for carbon disulfide linear because there are 2 electron domains where both electron domains are bonding. Molecular geometry for H2S is going to be single bonded hydrogens, 2 hydrogens, with 2 lone pairs on the sulfur. Now, how many electron domains are there? 4. There are 4, out of which there are 2 bonding pairs and 2 lone pairs. We refer to the electron domain geometry as tetrahedral, but molecular geometry as V-shaped or bent. I did mention just now the reasoning behind the shapes. That's because carbon disulfide has 2 electron domains, while hydrogen sulfide has 4 electron domains, out of which 2 bonding pairs competes with 2 lone pairs. I'd like to talk about how carbon disulfide and hydrogen sulfide are very similar to carbon dioxide and H2O. Why is that? It's because sulfur is an element just below the element oxygen. They both belong to the same group, 16. And what properties do the elements in the same group have? They have similar chemical properties. Just like oxygen bonded to carbon dioxide, to carbon in carbon dioxide, so will sulfur. Just like how oxygen is single bonded to 2 hydrogen atoms with 2 lone pairs, so will sulfur. So sulfur has 4 different mass isotopes, and the lowest mass isotope, 32, has by far the highest percentage abundance. Therefore, we would expect the relative atomic mass to have a value close to 32. But specifically working that value out, we would need to do 32 times 0.9 plus 33 times 0.01, corresponding to 1%, and then 34 times 0.04 plus 36 times 0.05. If we do the math, this all comes down to a value of 32.29. Apparently, the 36 mass 36 isotope has percentage abundance that's a lot lower, 0.01%. So if we want to work out the number of sulfur atoms within 1 grams, what we'll need to do is first work out the amount of sulfur in 1 grams, and then take 0.01% of that, multiply by the Avogadro's constant number. So let's start off with the amount of sulfur, natural sulfur in 1 grams. N equals m over big M, where mass 1.00 grams will be divided by the relative atomic mass of sulfur, 32.07 grams per mole. Then we will multiply this number by 0.001%, which will give us the mole, the amount of mass 36 isotope, and we'll then multiply the number again by 6.02 times 10 to the power of 23, which will give us the value of 1.88 times 10 to the power of 18. And the unit now will be atoms. If we want to work out the crystal structure of beryllium, we'll use X-ray crystallography. Easy question. Then we're going to outline how beryllium crystal structure is, in a sense, the metallic structure of consisting of lattice of beryllium cations surrounded by delocalized electrons, which is the electrostatic attraction between lattice of beryllium 2+ cations and delocalized electrons. Beryllium chloride is an electrolyte in molten state, where at the cathode and anode, we will be having beryllium and chlorine produced respectively. Molten beryllium chloride is going to be an electrolyte for one reason, because contains Be2+ and Cl- ions that are mobile and can move towards, for beryllium 2+, cathode, and Cl- to the anode. Beryllium would be migrating, would be attracted to the cathode, yes. Cathode attracts. Cathode is an electrode that attracts cations by being negatively charged. Which means that in the anode, we'll have positive electrode attracting the anions, where the anion, Cl- would be oxidized to Cl2, releasing electrons. Let's go with 2 chloride ions, liquid state, turning into gaseous chlorine, releasing 2 electrons. We have specified amount of current flowing, 1,000,000 coulomb, which means that we will have 1,000,000 divided by the Planck constant, 96500 coulombs per mole. Number of moles of electrons. That's 10.4 moles of electrons. The number of moles of electrons used to reduce beryllium 2+ is 10.4 moles. What's the significance of that? It means that because liquid beryllium 2+ ion is reduced by 2 moles of electrons, 5.2 moles of beryllium 2+ would be reduced by 10.4 moles of electrons to become 5.2 moles of beryllium solid. 5.2 moles of beryllium solid corresponds to the mass of 5.2 mole times 9.01 grams per mole. The relative atomic mass of beryllium, 9.01 grams per mole. So overall, we will have 46.9 grams. Beryllium chloride would be a linear compound, linear molecule that have 2 electron domains that are 2 bonding pairs, with chlorines having 3 lone pairs each. Beryllium, no lone pair. It's okay for beryllium not to have any lone pairs because it's one of the exception atoms to the octet rule. Beryllium chloride molecule therefore will differ from most Lewis structures in not having the full octet. Although it doesn't have to have the full octet, it can have the full octet. And one way to achieve a full octet or close to full octet is to have coordination. Specifically speaking, one of the lone pairs of chlorine would coordinate to the beryllium atom. So the way this happens is I'll call BeCl2 in blue color monomer 2, and I'll call BeCl2 in orange monomer 1. Chlorine of monomer 2 would coordinate to beryllium of monomer 1, while Cl that's adjacent to the beryllium of monomer 2 have one of its lone pair coordinate to the beryllium. So overall, beryllium will have 3 bonding pairs, and we want the 3 bonding pairs to be positioned as far apart from each other as possible to minimize repulsion. And according to the VSEPR theory, we want to opt to the trigonal planar structure, for which we want 3 orbitals, and to form 3 orbitals we would need sp2 hybridization. We have just mentioned how beryllium of monomer 1 acts as the Lewis acid being coordinated by chlorine of monomer 2. Acting as the Lewis base. Electronic structure, configuration. Transition elements will all have incomplete d orbital. That means looking at the first transition element row, starting with scandium, titanium, vanadium, and so on, copper will just about qualify to be a transition element, but zinc will not. In terms of electronic configuration, what we can tell is that all transition elements will have incomplete d orbital. Partially filled d orbital. And that's why zinc is not regarded as a transition element, but just a d block element, because it has full d orbital. We're going to explain the variable oxidation states property of transition metal with the example of iron, comparing the successive ionization energies with beryllium. And beryllium shows how there is a steep rise in the ionization energy from 2 electrons lost to 3 electrons lost. And that's because beryllium has 2 valence electrons, so that the 3rd electron being lost is from an energy shell that's lower in energy, closer to the nucleus. Hence the sharp increase. Sudden increase in successive ionization energy. That's between 2 and 3. And this contrasts with the gradual increase of Fe. That's the first point we should note. The second point is going to be how, if you look, for both beryllium and iron, they pretty much have identical first and second ionization energy. And the gap is very small. The difference between the first and second ionization energy is very small, which means that the metals will not form +1 ions. That's another point we can make. And finally, for iron, the third and fourth ionization energies are close to the second. Therefore, iron can lose different number of electrons. Cell potential. We're going to calculate the cell potential. How? E theta equals to the electropotential of cathode, take away the electropotential of the anode. What's being reduced at the cathode? It's the water that's being reduced at the cathode, with electrons released from the oxidation of beryllium at the anode. So, what is the reduction potential of water? Let's have a look. Reduction of water has the potential value of minus 0.83, which would be which we will minus with minus 1.85, the reduction potential, the standard electropotential of beryllium reduction. Therefore, overall, we'll end up with 1.02 volts as our cell potential. Yes, it's a positive value for which we would expect the redox reaction between beryllium and water to be spontaneous, because according to delta G equals minus NFE, positive E theta renders negative delta G value, which corresponds to spontaneous. All spontaneous reactions have negative delta G values. We expect the ionization energy to increase across the period generally. From lithium to beryllium, definitely. Why? Because the nuclear charge increases by +1 plus charge. That's because beryllium has one more proton than lithium. However, beryllium also has one more valence electrons. But valence electrons do not contribute to the shielding effect by the inner electrons. The shielding effect is of equal size for both lithium and beryllium, which means that the effective nuclear charge is higher for beryllium. What's effective nuclear charge? Effective nuclear charge is the number of protons minus number of non-valence electrons that are shielding. So the electrostatic attraction between the nucleus and the ionized electron will be stronger for beryllium. Let's write that down. Nuclear charge higher in beryllium, which has equal shielding effect as lithium. Therefore, electrostatic attraction between the nucleus and valence electron stronger. But unfortunately, there's an exception. From beryllium to boron, there is not an increase, but decrease. There is a reason for that, and that's because the electron being lost from boron is at a 2p orbital, where beryllium has the electron being lost from 2s orbital. Now, what's the difference between 2s and 2p? 2p is more energetic, is at higher energy than 2s, which means that the electron within that 2p are further away from the nucleus and therefore more easily lost. Let's put that into writing. Boron has ionized electrons, removed from 2p orbital. That is higher in energy than 2s orbital of beryllium. Therefore, less energy required for removal of 2p electron to infinity. Remember how line emission spectrum shows lines that correspond to discrete energy levels converging. Lines converge towards limit at higher frequency. Eventually, there will be a line where we cannot have higher frequency, and that corresponds to the ionization energy. Therefore, the first ionization energy of beryllium would correspond to frequency at a line of convergence. We start with a compound that has a benzene ring, but by nature it's an alkene. There's a double bond, which reacting with water and sulfuric acid, which is the catalyst, we will have an electrophilic addition reaction where water will be acting as the electrophile that will eventually be integrated to the molecule, to the reactant molecule at the sacrifice of the double bond. Therefore, we will have a molecule that has now an alcohol functional group. It will be an alcohol with a benzene group. Which is stereoisomeric because the central carbon is chiral. Chiral because there are 4 distinct atoms and groups bonded, starting off with hydroxyl, benzene, methyl, and hydrogen. Chiral carbon atom that has 4 different atoms, groups, covalently bonded. The benzene ring substituent containing alcohol, our intermediate X, can be oxidized to a ketone. As a secondary alcohol, why secondary? There are two alkyl groups right there. As a secondary alcohol, there can be oxidation to a ketone, which would require acidified potassium dichromate or potassium permanganate. However, there will be a minor product that is also possible to be formed, and that's because you are adding unsymmetrical electrophile water. Water is unsymmetrical, and so is our phenylethanol. Unsymmetrical alkene and unsymmetrical electrophile will result in a major and a minor product according to the Markscheme rule, where the minor product would be a primary alcohol that looks like. Which will oxidize into an aldehyde and may further oxidize into a carboxylic acid. Carboxylic acid. So a carboxylic acid that can be drawn as we have drawn. That is produced due to primary carbocation that leads to primary alcohol. Nitration of benzene requires the production of electrophile nitro NO2 group, NO2 plus. And that's how prepared. How is NO2 plus nitro group prepared? By having sulfuric acid concentrated react with nitric acid. The mechanism would be to have the benzene ring, the electron-rich benzene ring, electrophilically attack a nitro group, the electrophile. Curly arrow needs to be displayed originating from the benzene ring, landing on NO2 plus, which breaks open to accommodate NO2, and hidden, there were a hydrogen hidden, but now we will display that, and a positive carbon, either on the left or right of the carbon to which NO2 is bonded to. More accurately drawing, we will have a planar benzene ring structure that has NO2 group on top or bottom of the plane with the hydrogen atom on the bottom or the top, opposite of the NO2. Then we will have the hydrolytic fission between the carbon and hydrogen that will contribute the shared pair of electrons back into the benzene ring to recomplete the benzene ring, which will now produce nitro added to the benzene ring. But let's not forget that an H plus has been produced, and that will probably be picked up by our reagents, sulfuric acid and nitric acid. Final question of the paper, finishing off with activation energy EA calculation, where we're given two temperature data and ratio of two rate constants. Let's have a look. So we have T1, let's refer to T1 as the initial temperature, 225 degrees Celsius, which we will convert to 298 Kelvin. T2 would be 308 Kelvin. The difference between the two will be that K1 and K2 will have the difference of 2 times. So let's say K1 is X, then K2 will be 2X. The equation we'll use to derive EA is going to be ln K1 divided by K2 equals to activation energy over gas constant minus 1 over T2, 1 over T1. Let's apply our values. ln K1 over 2 would be ln half. X over 2x, a half, equals to unknown EA over 8.31 joules per mole per Kelvin, bracket 1 over 308 minus 1 over 298 Kelvin. So we will divide ln half by the fraction in the bracket and multiply the value by 8.31 to have EA value calculated in joules per mole. It's joules per mole because the gas constant has the unit joules per mole per Kelvin. If we do the math, we will end up with 52868 joules per mole, but we are asked to calculate our value in kilojoules per mole, so 52.836, therefore 52.9 kilojoules per mole.